First of all, we got the Gaussian integral. Integral from negative infinity to positive infinity of e to the negative x squared. Very famous, this one. And the answer is also very cool. No elementary antiderivative. We're not going to do it that way. For this one, we use polar coordinates. Now, the way we do this is we would call this I, right? So let I equal to this integral we have here. So the integral from negative infinity to infinity of e to the negative x squared dx. Since both of the bounds are stated as numbers, numerical values, this is just a number. And if we square it, then it's just multiplying it with itself. So, if we square both sides, I squared is equal to, well, of course, we're going to have negative infinity to infinity, e to the negative x squared, and then we're going to multiply with another one times negative infinity to infinity. However, here, I'm not going to use x, I'm going to use y. The reason why I can use x and y and it's because they still represent the same value, right? The graph is, regardless, it's going to look something like this, right? It's going to look like, it's going to be a bell curve. So regardless of whether you call this the x-axis or the y-axis, either way, it's going to be the exact same number. It's going to be the area under this curve from negative infinity to infinity, okay? So that's why. So instead of using x, I'm going to use y. So instead of e to the negative x squared, I'm going to say this is e to the negative y squared, and then dy. Okay, now why do we do this? Well, notice that in terms of x, this y integral right here is just a constant, right? It doesn't have any x's inside. So kind of like how you could do a times the integral from, a to b of f of x dx, kind of like how this is equal to integral from a to b, and you can drag the a inside since it's a constant multiple, right? So you could integrate a f of x dx with the same bounds, and it's still going to be equal. Well, here, we can do the same thing. We can just treat e to the negative y squared as our a and drag it inside, since it's just a number. It has nothing to do with the x world. So let's put this on the inside. And I'm going to walk through this slowly here, since last time I didn't do a very good job of explaining why this is true. Alright, so now we can put this inside, right? So I would say, let's put it down towards the front, e to the negative y squared dy, right? So this is our constant, and then we still have the rest of our x integral. E to the negative x squared dx. Alright, now notice that you can think about it the same way, right? This e to the negative x squared has nothing to do with this y integral on the inside, right? It just represents a function in terms of x. So you could treat it as a constant in the y world. So let's drag it inside, right? Because you can always bring a constant inside. So this is equal to integral from negative infinity to infinity of the red integral from negative infinity to infinity of. So in here, we drag the e to the negative x squared to the inside. Notice that because these have the same base and they're being multiplied, you can add the tops. So you would get negative x squared minus y squared, right? And then, you can just have the dy be on the inside, and then the dx. So just like that, I've kind of justified combining these two integrals. That's kind of how that works. All right, now what we can do is in the exponent, we can factor out a negative. And then you can see where this is going. So we factor out a negative, and this inside becomes positive x squared plus y squared. dy dx. Like that. Now, well, we have an x squared plus y squared. Does that mean we can use polar coordinates? Absolutely. So let's let me introduce how to do polar coordinates again. This feels all too familiar. Okay. So in polar coordinates, basically, instead of counting well, how far you're going this way, right? So that would be like, say, A, and how far you're going this way, I call that B, right? And then this would be AB. No, we don't like go out in one direction and then out perpendicular. It's not like that. Instead, the way we do it in polar coordinates is first, we take the origin, right? We turn a certain angle from, a certain angle from the positive x-axis. So that would be like here. Right? So we would call this theta. And then this line has length r, and it would reach out to any point. Right? Right, so, and that's kind of where AB was, you know. But, yeah, that's how we measure stuff in polar coordinates. We turn, and then we stretch. And that's theta and r. So we have two variables. And why is this nice? Well, if you think about it, the way you would express the variable x in terms of r and theta, well, r, if you project it in the x direction, this right here is just r times the cosine of theta, right? And then this, if you project onto the y-axis, this is r times the sine of theta. So y is equal to that, and then x is equal to this. So that's what x and y are equal to, and then you can do some manipulation, and you'll figure out why this is really cool in a second if you don't already know what polar coordinates is. Okay. So let's put down some change of variables. Let's do that down here. So you would let x equal to r cos theta. Y would be equal to r sine theta. That's just a projection of, well, you can call it a vector. You can think of it as a vector, right? And it has its components, its magnitude, and its direction. Yeah, so we have that. Now, what about your differential? Because if you write it in terms of r and theta, well, you can't integrate with respect to x and y anymore, right? So how do we do that? Well, we're going to use something called the Jacobian. And it's basically a way of finding your differentials, but with more than one dimension. So we're working in 2 dimensions, right? So let's go ahead and use the Jacobian. Now, the way Jacobian works is, if I can get this right, so we notate it, the derivative of, in this case, we have yx, right? Since we have dy dx, over, well, and this would be a partial, actually, because we're working with multiple independent variables. So partial yx over partial, and we're going to be in the r and theta world. So partial r comma theta. This is just shorthand notation. You can't really tell what it means, right? So I'm going to expand it out for you guys. This means the absolute value, and I'm going to notate it as like this, right, of the determinant of this matrix, and it's called the Jacobian matrix. However, the Jacobian itself is just the entire expression. So the Jacobian matrix is the partial derivatives of each of these variables, each of the old variables, with respect to each of the new variables. Yeah. Okay. So, if we have, then we would have partial y, and then partial y in the first row, and then partial r in the first column. So partial y, partial r, partial y, partial theta, and then here you have partial x, partial r, and then partial x, partial theta. Yeah. Okay, so from here, we're almost done. We just have to multiply on the dr d theta. Notice that the dr d theta are outside of the absolute value, since absolute value of dr d theta is gonna make the whole thing positive. Okay, right. So this right here represents this part, right? So the way you would say it is, well, this is actually, it would be equal to dy dx. Yeah? So you would replace the entirety of dy dx with this expression right there. You're yet to evaluate. And all right, let's go ahead and evaluate it then. So in our case, this is equal to the absolute value of, and I'll put down the determinant again. I'll fill in these spots with whatever the hell they are. Partial y, partial r, take y, differentiate with respect to r. r is your variable, so the variable disappears, and then you have sine theta. So here you have sine theta, partial y, partial theta, differentiate with respect to theta. The derivative of sine with respect to theta is cosine. And the r is just a constant, so it stays. So you got r cos theta. Partial x, partial r, right here. R is your variable, cosine is your constant, so the cosine is going to stay. And then here, partial x, partial theta. Well, r is a constant, right? And then the derivative of cosine theta is negative sine theta, so you have negative sine. Negative r sine theta. Close everything, dr d theta. Right. Okay, and from here, calculate the determinant, this times that, right? So we've got the absolute value of sine theta times negative r sine theta gives you negative r sine squared theta. And then you have to subtract off the other diagonal, minus r times cosine, r cosine squared theta, dr d theta. From here, factor out a negative r. And then after you factor out the negative r, notice that you just have sine squared plus cosine squared left, which gives you 1, so we're not going to write that down. Absolute value of negative r, which by the absolute value property, you can split up into negative 1 times r. Absolute value of negative 1 is just 1, so you just get absolute value of r left, which is just r. So this, in summary, gives you r dr d theta. So, well, I'm going to write it like this, dy dx. This is just shorthand notation. I'm going to get rid of this. But that represents the absolute value of the determinant part. Dy dx is equal to dr d theta. And this is always true when you're going between Cartesian coordinates, which is x and y, and polar coordinates, which is turn and reach, basically. Angle and distance. So, yeah, we can go ahead and plug everything in now. Okay, the bounds are a little bit more finicky. Right. Let me think about how you would actually do this. Okay, you know what, it's fine. So, let's plug this all in. The bounds, well, they're finicky, right? So we're going to leave them for now. You have your integrand, e to the negative x squared plus y squared. Well, x squared plus y squared is equal to this guy squared. So r squared cosine squared plus y squared, which is r squared sine squared. Once again, factor out the r squared. You have cosine squared plus sine squared left, that's just 1, so you just have r squared. So x squared plus y squared is equal to r squared, and you can see why that's nice. Well, you may be wondering, this just gets us back to where we were. Are we going to do this with differential? No. We have our differential here, right? Well, our Jacobian here, and it's r dr d theta. So this presence of this r right here makes it such that we're able to do a substitution, because in the argument of the exponential function, let that be a new variable. Before we do any of that, we still need the value of our bounds. Now notice that the inner integral is is with respect to r, right? So you need something r equals something. Now, if you were to graph this out, we're reaching in the y, so the red bound in here, the y bound, it goes from negative infinity all the way up to positive infinity. So the y value spans the entire plane, right? So does the x value. So you're covering the entire xy plane. And how would you express that in r theta? Well, first of all, how far would you have to turn? You would have to turn all 360 degrees to be able to cover everything, right? So you would go from 0 to 2 pi in terms of theta. So theta would be 0 to 2 pi. All right, starting from 0 and then turning 2 pi radians all the way back. So r, it would have to be infinity, because you're sweeping all that direction, but you also need to reach infinitely out and sweep like that. So this would be from 0 to infinity. Right. Okay, now, what can we do? Yeah, okay, let's go ahead and integrate, because notice that you can just make a substitution, and do stuff like that. And I'm going to erase this now. I'm going to do all the work over here. So I'm going to erase everything having to do with our substitution, or not substitution, just changing variables. So, before we do any integration, I want you to notice that in here, this r guy has nothing with the theta in it, right? You're going from 0 to infinity, no theta, e to the negative r squared r dr, no theta, right? So this is really just a constant inside of this outside integral, this theta integral. So you can take it to the outside. Think about it like that. So let's keep going. So let's take this guy outside. So you have integral from 0 to infinity, r times e to the negative r squared dr, and then you have this integral left. So bound in the theta. That's basically it. So you're multiplying by integral from, the bound was 0 to 2 pi, and then it was just d theta. Okay. In here, let's make a substitution. In fact, let's multiply it 2, and then divide by 2, right? So, in fact, before we even do let u equal to r squared. All right. So we have our 1/2, have this integral. And yeah, let's use the variable u, okay? 2r dr is going to be our differential. We can just ignore the 2r for now. And we just have e to the negative r squared is just u. And then we let the 2r dr be our du. And the 1/2, of course, is sitting outside. What are the bounds? Well, these are in terms of r. We want them in terms of u. So r squared is equal to u. 0 squared is equal to the lower bound, right? So it's still 0. Infinity squared is still infinity. This one right here, we can just integrating theta in the theta world gives you theta. Plug it in from 0 to 2 pi, you get nothing remarkable. It's just 2 pi. So yeah, let's do this in the next step. So first of all, notice that the 0 is empty. Plug in 0 gives you 0. You would just plug in 2 pi. 2 pi is a constant multiple. You can take it to the front. Notice it'll cancel out with the 1/2, so you're just left with a pi by itself. This integral from 0 to infinity of e to the negative u du. Integrating e to the negative u, you just get negative e to the negative u. Plug in from 0 to infinity. Right, and then you would get, plug in infinity, e to the negative infinity. Well, if you notice that as e to the x approaches negative infinity, this is what the graph looks like. It's going to approach 0. It approaches the x-axis. So this guy actually goes to 0. Why? Okay, well, if I plug in 0, it's going to return -1, which is not correct. Is there something that went wrong? Okay, my bad. Because the top bound is 0, you do 0 minus the lower bound. Okay, so yeah, I tend to get that confused. So if you do minus negative e to the negative u, well, plug in 0 for u, e to the 0 is just 1, so you get minus -1, which is just a 1, and you're multiplying that by pi, so you're just left with pi. Notice that this is I squared. I squared, well, yeah, I'm going to draw an implication symbol here and tell you to notice that this is I squared. Well, if you take the square root on both sides, since we know that, well, the area isn't below the curve, it's above the curve, well, then I by itself is just the square root of pi. So the area under the bell curve found using the Gaussian integral is just square root of pi. So that is the first famous integral. Pretty cool, pretty cool, pretty cool.